Data analytics. This course, operations research is under another umbrella that's called data analytics, and you hear about that everywhere, especially nowadays with AI and stuff like that. So data analytics has three main branches. One is descriptive methods. One is predictive methods. Predictive analytics, data analytics methods for models. And the third one is prescriptive. To put it in simple terms, descriptive models help you see what's going on by looking at data. And common tools are the basic statistics and data visualization. And then, like histograms, all sorts of charts, pie charts, everything that summarizes the data. And then we have predictive models or predictive methods. They're going to tell you what's going to happen. And machine learning, regression, and even classification methods. Yeah. Basically, they are smarter. They are not only they describe the data, they also, I may put classification under descriptive, but they're gonna help you predict what's gonna happen in the future based on what has happened in the past. And I don't want to get into the distinction between forecast and prediction, but generally speaking, they're going to tell you what is going to happen. Forecasting is based on previous trends. Prediction is based on the mechanism, understanding how something is going to develop. If I were to use the same method here, what's going on, what's going to happen, what do you think I will write here for prescriptive data analytic methods? What's happening? That could go probably on the descriptive. What it has a what, but what do you think? Like by looking at the data and making models, think about AI or all the things that we have. These tools are helping us summarize, know what's going on. They can also help us understand what's going to happen. What else do they do? Like all this new technology and data, there is something else that they do that falls under this category. What? For example, when you use Google Maps, what does it do? It tells you what to do, which route to pick, or it gives you alternatives. Or
decision making.
What is it?
Decision making. No.
Decision making. Yes. What to do, basically, like you said, make decision making. Here, the tools that we have are optimization methods, that again is either deterministic or stochastic. Deterministic meaning for a set of givens that are known, what is the best decision to make? This is my origin, this is my destination. It's known. What is the best route? It calculates the best route from this origin to this destination. Or I want to visit this many customers today. What's the shortest path among them? Their locations are known. But what if that's deterministic model? But what if their locations are uncertain? I may have a customer here, or the location may be here or there, right? The distance to this customer, depending on traffic, it may be an hour or an hour and a half. And it's funny, these are very similar to how we think these models. When we try to basically teach the computer, think like how we do. And these models are considered this like as you go from top to bottom, they become more difficult. So these are more advanced and more difficult to these models to build and run and optimize. We have models that optimize optimization models. That's a different story. We'll talk about that later. But yeah, so this is the idea of where our course stands in terms of the general broad area of data analytics.
Seems a skill set to train the AI.
What is it?
Seems like a skill set to train the AI stuff. Look like it.
Mm-hmm. AI does a lot of these things. I'm not an expert in AI or in large language models, but they are pretty advanced. And I've tried to use AI to even make generate mathematical models for the type of things we do. They are not still there to do that, but they are pretty advanced and they can do a good job, generally speaking. But they are still not there. If they were, most of the world problems would be solved. Because you'll understand by the end of this course why AI cannot solve the problems. Why? Because when you want to solve the problem, you're not here or here, you're here, right? And solving a problem requires a very accurate and comprehensive model. And to make that model, for it to make sense, you need to, it's very difficult to do that. When you make a mathematical model, basically you're finding a very accurate way of describing a problem in a way that nobody else can misinterpret it. It can be interpreted only in one way. That's why we use math. So first we want to learn about model building, and then we want to learn about solution methods. We'll spend a few sessions on just building models. And when I say model building, what I'm saying is we need to describe the problem with math. Our models are mathematical. And yeah, I'll talk about models later on. So prescriptive or optimization models, we're talking about these, and you know what that means now. These models usually have 4 components. The models that we build have 4 components. The first component is an objective function that's trying to maximize or minimize something. And then we have parameters or data, and then we have constraints or real world. limitations, and then we also have decision variables. Okay, before I get into these, let me ask you to do something. I want you to, you all use Google Maps, right? Or Apple Maps on your phone. I want you to take out your phone from your pocket and put your home address, or not your home address, somewhere else that's more, that can have multiple routes to it. Like put a destination there, and then select one and then hit go. And then I want you to explain what happened in your brain. Like this is something you do every day, right? So I want you to monitor what's happening in your head, like all the steps. Like imagine you're training a robot to do, like there is a robot that exactly does what you tell it to do. How would you describe the steps you ask that robot to follow? So here I'm gonna put Pomona, California 2, for example. San Francisco. Okay, this is what you did on your phone, right? So what was the first thing I did, or you did? Like you want to write an instruction for the robot to do exactly what, like we want to train a robot to use Google Maps, or someone who hasn't used Google Maps before, like a friend who hasn't had a phone yet. They were in prison for 20 years and now they're out. You want to teach them how to use Google Maps, right? What should we do?
Type in location.
So step one, what do you do? After you open Google Maps app. Two, what should they do?
Type in location.
Enter
Starting location.
starting and end locations. Then hit solve, hit find. And then what? So am I done here? Have I made this, has the decision making process completed yet? I have to pick one of these, right? Pick one route, right? Pick one path and then go. All right, this is the process. Now I want you to describe this to that robot because they don't know anything. They say, how should I pick one? There are three things here. How do you pick one? Let's say you're going to San Francisco now, or tomorrow morning, or how would you pick one?
What the mode of transportation?
What is it?
Selecting the
Mode of transportation.
Yeah.
So you consider mode of transportation, which is usually, let's say it's a car. So you know that in your head that you're gonna use a car, you're not gonna walk or use an airplane or ship or that, you know that you're gonna use a car. What type of car? EV or yes, or that's important. Why?
You have to recharge.
You wanna know like where are the charging stations? It's long distance. What else do you consider?
Duration.
Travel duration. What else?
High road, freeway,
Hmm?
high roads, highway.
Type of road
Yeah.
or like sceneries? Or if whether there is construction or not, or in general, road type. Sceneries or whether it looks beautiful or not. And
Start time.
the start time.
I have like a fuel efficient tag on the map. I don't know if it's beside.
What is it?
They have like a fuel efficiency tags on the map. I don't know if it's
Tax?
the gap.
Fuel?
Yeah, fuel
Aha,
efficiency.
okay.
Yeah.
Yeah, like cost of some roads are faster, but because of less traffic, but they're longer, right? So yeah, you consider all of these, but how does your brain work in? Because you're gonna pick one of these, right? How does your brain work in picking these? Like, yes, all this information is involved, but how do you organize this information? You know, because you do that in like less than a second, but you still go through a process, and you want to teach that to a robot that or computer that doesn't know anything. How do you explain that? Like how? So you ask the robot, get this information, right? Now the robot knows, and then says, okay, how do I use these to pick one path out of three? Road type, views, okay, I checked everything.
You would rank the criteria.
Uh-huh. Okay, you want to rank them. So I wanna put these, collect the data, and these are the data for each route. Before that, find possible. So when you say when you hit find, what happens is it finds all possible routes or paths. Then to choose them, collect data for each path. You collect it, and then when you want to pick, you're instructing the robot to do that. What did you say? You said have a criteria,
Yeah, to rank them.
use a criterion to rank them.
Some people like a short duration, some people like a safer road. So
Like cost, fuel cost. So you have a criterion that helps you decide which one is better, right? For example, let's say it's time, duration. That's what we usually pick, right? Duration, and then what else? Hmm?
road type.
So what Google Map gives you is not a prescriptive model. It doesn't tell you what to do. It doesn't tell you which route, where to go. Let's say you want to create a new app using that robot or computer that is prescriptive, which means actually selects the route. Like you don't have to go through the process to go to Google Map. You just say I want to go to San Francisco, and it says go. It has already picked the best route. We want to make that algorithm or that computer robot that does that, right? So what Google Map does, it just finds all possible paths, but then you have to choose. So it's not prescriptive, right? We want to add the prescriptive component, which is this part. Pick one path. So the first step, find also all possible paths. Second step, collect the data. Third step, use a criterion, for example, duration. Then what? Rank them. Pick the best one. Pick the first one. But if you were to but something else has also happened here that goes unseen. What is that? When when you hit find, here I wrote a word, find all possible path, right? But if I didn't have that possible and it showed me all the routes, what else would you see here? Here you would probably see all the this is already filtered, like these are the set of best path, right? It's not all the possible path. Like there is one, you go up here, then you change here, then you go back, then you go up, and then these are basically already very good path, right? Also, it only shows paths that are suitable for a car. Where is that? Here. For a car, but if I select here that I'm walking, it changed to something else, right? Which was mode of transportation. So here, when you said use a criterion to rank them, here I should write based on mode of transportation. That's more accurate. Transportation. Okay, this is what our mind does in a fraction of a second. But that's how all optimization models work. And we want to keep that in mind. And let's go back. Here we're talking about components of an optimization model. Every optimization model has an objective function, maximization or minimization. What was our objective function here? Minimize travel duration, right? Based on that, we pick the path. Every optimization model has some parameters. What were the parameters? Pomona, San Francisco, and also all the data we collected about each path. This has suitable for walking, this is suitable for a car, and this one has these many fuel stations, gas stations, this one has this many charging stations. This is all the data, right? The data, or that we call parameters.
So the data will come from the environment, not the entity itself, right? I mean the user, right?
Data is anything related to the problem,
Okay.
right? And then we had some constraints. We always have some constraints that are based on real world limitations. So in our case, the constraint was we are having our mode of transportation is a car. A car cannot drive up mountains, right? So it cannot fly. That's a constraint. When you're picking a path, don't just pick all the routes between point A and B. Just look at the ones, just filter out the ones that are not compatible with the car. Then out of those that are within the constraints, that comply with the constraints, that don't violate those constraints, then pick the best one that maximizes or that minimizes the travel duration or minimizes the cost or maximizes the joy of travel, which is having sceneries and views and being able to take pictures, have good weather and a lot of shops on the way so that you can stop by, for example, and enjoy the travel, the road trip, or you get good signal. You see, there are so many things you consider based on your objective function. So a lot of problems just like that. So what was the thing that made this an optimization problem? It made it a problem. I can call it a problem. What, like, if I had only one route, let's say from Pomona to San Francisco, there is only one path, not multiple. There's just one. Can you choose anything? No. There is no choice. The problem comes from having multiple choices, right? And Google has made your decision-making problem simpler by filtering out a lot of choices so that you're stuck with just two. If it showed you like all the actually possible routes between Pomona and San Francisco, it would go, for example, from here all the way to, I don't know, to Frenzo, and then why not that? And then it would go to, what is it? You may go to Utah or Las Vegas and then to San Francisco. There are so many different paths between these two, right? It's like a graph, and these two nodes, there are so many ways you can go from one to another. But it is already filtered out, the set of options.
See that you can go to Malibu and then drive up there.
What is it?
See that you can drive to Malibu and then we roll up to San Francisco.
Malibu.
Yeah.
Yeah. So it is already filtered out, but what makes it a problem is having many options, having choices. If we didn't have a choice, let's say this is all a desert, right? And there is only one path from here, like one road that goes from Pomona to San Francisco, and that's it. Then it wouldn't be an optimization problem. Just go through that road, that one road existing. So what makes this problem? What makes these situations problems that we need to optimize is that we have multiple choices. And these are examples of such cases these are famous problems or problems encountered in industry a lot or businesses. I'm gonna go through them quickly. But before that, let me give you a break for 10 minutes. And when we're back, we'll continue. Okay. Okay, welcome back.
So I think the code in the restroom is changed. I use the blueberry one, which is 354.
What is it?
The restroom code. Yeah, the 4132, I think they changed.
45 3545.
3545.
I think that's the correct.
This one, right here.
Yeah, this one.
If they change it 354, that's it.
3545. Yeah.
It says 3 on the board.
Huh?
I think that's wrong on the board. Yeah, 3 on the board here.
All right. So I'm going to go over some important optimization problems, explain to you in simple words what they are. The main reason I'm doing this is to see if it reminds you of similar problems that that apply to where you work at or what you have seen before. So the first one is vehicle routing problems. VRP. VRP applies in general to problems where you want to find the optimal path going from one point to multiple points and then come back to the original point. Let's say you are a distributor of bread among or some meat among like multiple restaurants, right? Or milk to coffee shops or whatever. You have to go, your start point is the factory, and you have to go visit a bunch of stores around the town and then come back, or multiple towns. We had a problem like that actually for I forgot what type of business it was. Yeah, so you have many different options, which town to visit first, and then within that town, which store to visit first, so that your overall time of travel is minimized, or the overall path fuel expense, fuel cost is minimized. That one has numerous applications. In Amazon, when they have a truck filled with orders that they want to deliver, they have so many addresses, right? They have to run these models that to ensure that the path they go through is optimal. Again, why is it an optimization problem? Because you can do that in many different ways. The next type of problem is single machine scheduling, patient scheduling, crew scheduling. For example, a single machine, you have one machine and multiple jobs that need to be processed on that machine. And those jobs have different processing times, and they have different due dates. Here, the options are in what sequence you're going to process this job. Which order will be processed first? Again, your objective function could be minimizing due date penalties, minimizing make span, and we have a lot of different types of problems under this category. Fleet replacement. Let's say your company or your organization has a group of identical machines, such as trucks, or an airline has multiple airplanes, and they have a flight load, or a construction company has multiple loaders or dozers. They need to, and they have a flight load or operations load that these machines need to work on for the next 10 years. And these machines have a lifetime, and as they age, their maintenance costs, operation costs go up, and their value decreases. And what is the optimal schedule for renewing your fleet, or when to retire each specific car in each specific item, which could be an airplane, a vehicle, a truck on your fleet. I have multiple papers in this area, and also in single machine, and also vehicle routing problem. I have just one paper as a co-author, but this is an area I'm working on right now. And then we have flight and maintenance planning. I'll explain that in the next slide, in one of the next slides. Or we have team formation. Let's say you're at a company, you're working with many different people, they have different skill sets, and for each different skill, they have different competency levels. Let's say in terms of CAD, CAM, SolidWorks, one person is average, one person is really advanced. In terms of programming, that person is average, the other one is advanced, and you have, let's say, 20 people like that. And you're trying to form a team for a specific project that requires multiple skills. And you need to optimize either competency, or whether these people get along, or cost of hiring them. Those could be different objective functions or criteria. I had one student in this class, 2021 or 2, I can't remember. He worked in aerospace industry, and he developed a model here based on a model that I had developed before. Sent it to IIC, the conference, and he won the best student paper. And he also turned it into his master project. So that was in this area. Supply chain network design. Why do you think supply chain network design is an optimization problem? First of all, what is supply chain network design? What is the network in a supply chain? Let's say I am making a product. It has 100 items in it, 100 parts in the bill of material. And then for each part, or the parts have multiple suppliers. And suppliers may have overlap in the types of parts that they supply. And then you have retailers. Then you have distributors, retailer stores. So this creates a network. And you have different manufacturing plants across the country or in the world. Should you work with all these suppliers, or should you select a few? Should you work with all these manufacturing plants for all the products, or should they specialize in a few of them, depending on which top suppliers are closer to them, right? And then which retailers should sell what, depending on the demand of the customers. So these nodes essentially create a complex network of suppliers, retailers, distributors, and manufacturing plants. So how much should you supply to plant A from supplier A, and how much from supplier A to plant B? And how many units of each item? So it's a decision to make, and there are so many different ways you can do that, right? So you make a model in the computer, you put in the data, these are my suppliers, these are the costs, these are the distances, these are the locations, these are my manufacturing plants, these are my products, this is the bill of material, and these are my distributors, these are where my customers are, retailers, and hit the button solve, and it will tell you exactly what's the optimal number of each item to order from each supplier. That would be a supply chain design, a supply chain network design problem. Or reliability allocation. Let's say you're working on a product and you want to make it 99% reliable, which means the probability that it doesn't fail in the next 1 year, for example, is 99. You want it to be 99%. But when you do the testing, you realize the reliability is 86%, which means you're gonna have 14% return products, and it's too much for you. You cannot handle that. You want only 1%. So how can you solve that problem? You can add redundancies to the weak points where the components are more likely to fail. But you have multiple opportunities to do that, and you have a limited cost, limited budget to do that, right? So again, this becomes an optimization problem that tells you what's the optimal location on the design. And I'm talking about a complex product, not a product with just 3 components. A product with hundreds, if not thousands of parts. I teach also reliability engineering. In that course, we get into system reliability. And I think it would be really great if you could have that course also in your program, or at least somewhere among your courses. Do you learn anything about system reliability in industrial engineering? Yes. Not in this program, systems. In what course?
System life cycle.
Oh, system life cycle. Okay, that would be a good course to add it to. Like serial, parallel, complex configurations, and then how all those little reliability numbers add up to the system reliability.
Yeah, the tree.
Yeah, perfect. Yeah, that's the, have all of you taken it? You probably-
Making it right now.
Ah, okay. So that's another application for optimization. Okay. So as I talked to you about every optimization problem has 4 components: objective function, constraints, data or parameter, and decision variables. Let's look at a very simple example to explain those again so that you get an understanding of basic terminology. Our decision variables are, let's say x1 is flight hours of airplane 1, x2 is flight hours of airplane 2. Our cost constraints, and z, another variable, is total profit. So these are the things that, because they're variable, they create multiple options, and because of that, it becomes a problem, an optimization problem. And then constraints or limitations is, so by having these 2 variables, essentially, we'll have something that we call solution space, which means any point here that I pick, let me use any point in this area, in this 2D area, is a possible answer. For example, here, both x1 and x2 are 0, right? Here, x1 is 0, x2 is a positive value, for example, 10 or whatever, 10 hours. So this is essentially a solution. This point where my mouse is a solution. Why? Because just like those routes in the Google map, each one of them was a solution, and you had to pick the best one. Here, each point is a solution. This point tells you that flight hour of airplane 1 should be 0. Flight hour of airplane 2 is some positive number. This one says, this is a solution. Flight number, let airplane 1 and 2 fly each for 1 hour at this point. Here, 0 hours, both. So all of these are, all the points here, which we have infinite of those, are solutions. And we call this the solution space. Now we have a constraint. It says airplane 1 cannot fly more than 10 hours. So I add a constraint to limit my solution space. So this is not part of the solution space anymore. My solution space is only this area with that constraint introduced. Next one says airplane 2 also shouldn't fly more than 10 hours. So these points shouldn't be considered as solutions. So I add another constraint that makes sure that, so our solution space is now more limited. It's only this area. It still is very large. Also, we have another constraint that says x1 plus x2, or sum of the flight hours of these 2 airplanes, should be less than 15 hours. That would be a line here. So that further limits the space to this area. And then another one that says flight hours cannot be negative. For example, this point here is saying that flight hours of airplane 1 and 2 is -1. That doesn't make sense. So I need to limit those 2. Now the solution space is limited to only this area. That's my solution space. We call it feasible region, which is a, mathematically speaking, is a polyhedron. This feasible region, any point that you pick there does not violate these constraints. For example, here, 0, 0. 0 is less than 10, 0 is less than 10, 0 plus 0 is less than 15, and 0 and 0 are both greater or equal to 0. So This is an acceptable point. This is everything here is an acceptable point. We call this the feasible region. Now, the objective function says z, which is total profit, is 8x1 plus 3x2. Why, for example, we make $800,000 by flying every hour the airplane one, or 300,000 for 1 hour of flying airplane number two. So now we have a criterion, just like duration of travel. Now this is my criterion that evaluates all the points in this area and tells me which one is the best. So this here is a model. Call that a mathematical model. This problem precisely explains what I'm looking for, what is my objective function, what are the real world or constraints in the scope of this problem, and what are the decision variables. And as you see, these decision variables contain the solution, because when I give them values, they become solution. When x1 is 0, x2 is 1, that's a solution. The solution algorithm, on the other hand, is not shown here. The solution algorithm would search through this feasible region or the solution space in general and find a point or a solution that maximizes or optimizes this objective function, which in this case is maximization. And we have commercial solvers such as Groovy, Cplex, Excel solver, GAMS. These solvers have built-in algorithms that can find a feasible solution. So all you need to do is to give them your model. Hit solve, it will use one of the solution algorithms, solution finding algorithms to find the best answer, the optimal solution, if it exists. We'll talk about that later. What is an exact optimal solution? Exact means or optimal solution in general. What is it? It's a solution whose corresponding objective function is better than all other solutions. So this point, if you plug it into this objective function, this point, what is it? It's, for example, x1.5, x2, 2. If you plug it here, you get 4 plus 6, 10. 10 is the value of that solution. What is another solution? 1 and 1. If you plug in 1 and 1 here, you get 11. So 0.5 and 2 has a lower value for objective function compared to 1 and 1. Therefore, 1 and 1 is a better solution, but it's not optimal. Optimal is the one that's better than any other answer or any other solution. Near optimal means, for example, let's say I found a point here that whose corresponding objective function value is 20. All right. It is 80 actually. But let's say I find another point whose objective function value, when I plug it in here, is 78. If that's the case, it's actually 80 plus, it's 95. The optimal solution objective function value is 95. Let's say I found another point that gives me 92. It's close to that optimal solution, so I call it near optimal. And feasible solution is any point here. Any point here is basically feasible because it doesn't violate any of these. And then we have infeasible solutions. Points that are outside of this feasible region, those are called infeasible. So that point right there that you see, this one is optimal. Then we have near optimal solutions. What are these points? Blue ones. according to that definition, what are these blue ones called?
Feasible?
Feasible because they are within the feasible region. And then these are infeasible solutions. Make sense? So each point is a solution. What are decision variables? Decision variables contain the solution. They can contain different solutions. When you make the value of a variable known, it becomes a solution. Okay. So these solution algorithms that we have that search through this space to find that best point, if it exists, they have just like any product, they have different, in terms of performance, they're different. What is the criterion for deciding which algorithm is better or performs better? Some algorithms are faster. Some algorithms use less memory. So those algorithms are better. We would say that they perform better. The first algorithm takes an hour for it to find the optimal solution. The second algorithm finds it in a few seconds. So the second one performs better. But also some algorithms are not capable of not capable of guaranteeing to find the optimal solution. They just give you a feasible solution. But some guarantee that if the best solution exists, they can find it. It doesn't always exist, and we'll see examples of that.